The fifth pillar of calculus is that the whole change is the sum of the little changes. Now, I tried to come up with a snappier title, but I just couldn't think of anything. If you could think of something, let me know. So far what we've learned about is derivatives. We've learned that the derivative of a function is the rate of change of that function. It's how fast is that function changing. And we get that as a limit. Everything is closer is good enough. We get that as a limit as the interval that we're sampling over gets smaller and smaller and smaller of the function an instant from now minus the function right now divided by the length of that instant. And then we also learned about an integral. The integral of f of x dx from a to b was the total amount of stuff. Now, what we mean by stuff depends on the application, but technically what we're talking about is we take a sum as we chop things into n pieces, the function value at each piece times the width, and then we take a limit as we chop things finer and finer and finer and finer. And the big question is, what in blazes do these two ideas have to do with each other? We've got derivatives, we've got integrals, and they seem to be totally separate concepts. Now, in fact, there's this incredibly important theorem that relates the two. And this is called the fundamental theorem of calculus. And it comes in two versions, and I'm only going to give you one version today. We'll learn about the other version later on. The version that we're going to talk about today says that if you first take the derivative of the function and then integrate that derivative from a to b, you just get the value at b minus the value at a. So this gives us a really good way to figure out integrals. If you can find if you want to figure out the integral from 2 to 3 of x squared dx, you just have to find a function whose derivative is x squared. If you can find a function whose derivative is x squared, and x cubed over 3 does the trick, then you evaluate that function at 3 and at 2, and you get 3 cubed over 3 minus 2 cubed over 3, which is 19/3. Okay? You don't have to do all the messy business about taking limits. So why should this be true? Well, the idea is that if you want to figure out what is the change in the function between a and b, we've got a and we've got b. And we'll take a whole bunch of points in between. So we'll call a is x0, and then x1, x2, and b is xn. So f of b minus f of a, the total change, the amount of change from here to here, is f of xn, that's f of b, minus f of xn minus 1, plus f of xn minus 1, minus f of xn minus 2, plus all the way down to f of x1 minus f of x0. So the change from here to here is a change from here to here, plus a change from here to here, plus a change from here to here, plus a change from here to here, all the way across. Okay. But what is the change of a function from one point to the next? What's f of x0 minus f of x1? What's the function an instant from now minus the value of the function right now? That's the rate of change times how long you let it change. And we put it's approximately there because the rate of change times change is only good if the rate of change were constant, which it's not quite. But if you chop things finer and finer and finer and finer, in the limit, this becomes the integral of the rate of change dx from a to b, and that is the integral of f prime of x dx from a to b. So the change in the function, the total change, is the sum of the little changes, but a sum in the limit is an integral. And so we get the integral of the rate of change is the total change in the function.